Hello, everybody. I'd like to thank you all for being here to do our presentation for our senior design project, which is titled WMU Campus Parking Structure. This is a cross-department collaboration between the College of Engineering, UDMM, and TCU departments. Our sponsor is WGI, and our point of contact is Andrew Kong. This is the disclaimer. This is a student proposed project. And there's no actual plan unless it's
Thank you. I don't want to get in trouble.
So on Thursday, I'm in the EDMM department. I was responsible for developing the project schedule and detailed costs.
My name is Brian Graham. I'm in the TCE department, and I was in charge of structural and geotechnical.
I'm Andrew Lieto, also with the TCE department. I'm on the configuration of that project.
So on the agenda today, we are going to discuss our project overview, including all project goals and strengths. Then Brendan and Andy will dive into the traffic, structural, geotechnical design analyses. Then I will take over and discuss the construction management portion, which includes scheduling and estimating. And then please save all your questions for the end, as we will have sort of Q&A session. With that, I'll pass it over to Andy.
What you see in front of you is a parking map of a portion of West Michigan's main campus. The lots in the figure on the right are 72W and 61. These lots are extremely full. They're peak hours of the day. Any student here has George Parker knows the struggles that goes on with that. So for our project, we decided we'd like to construct a parking structure on lot 72 west to help relieve some of those stresses for students. A little bit more detail here. This is a protected construction site for our new structure. The goal is being designing a safe and cost-effective structure that will hopefully increase parking capacity by 50%, as well as introduce some green space to the area. Two important constraints we consider were time and cost. In addition to being a cost-effective structure, this is designed for student use, and we hope that we can use the summer months for construction, finishing around August before the fall semester. Briefly, our structural characteristics: it'll be a three-level structure. It'll have an entrance on the east side, level 1. There will be 4 stair towers in each corner of the structure. Each level consists of 2 flat bays and a ramp bay in the center to allow traffic to go up and down. Each bay consists of 2-way traffic throughout. For that, that requires some parking requirements of each stall width being at least 8.5 feet. That's no less than 18 feet. Width 20 feet. And the means of egress can't be more than 300 feet, meaning anywhere you stand on a parking structure, you can't be more than 300 feet from any existing exit or entrance, which that is well here. Our ideal site layout is to increase parking capacity vertically with our new structure, which includes 420 total spaces. To achieve our goal of increasing the slot capacity by 50%, we would need actually 510 spaces. To reach that number, we're going to utilize existing exterior parking shown in the figure. With that existing exterior parking and our construction of 420 spaces, we achieve 526 total spaces in the lot. Any exterior that is not used will be introduced as green space, approximately 14,000 square feet. Our analysis of alternatives include our structural material. It's important for us to understand what structure would best fit our project. The parking garages are typically built with steel, cast plate concrete, or precast concrete. These were the 3 materials we decided to analyze. Using this matrix here, we weighted each consideration for 2 most important considerations were construction time and cost, which are weighted slightly higher than the rest. And as you can see from the total score, the highest number being the most preferred material for our fabric, that being precast concrete. We chose precast concrete because it's lower cost, better constructability, and has shorter construction times, which would help meet our goal. We're going to hand off to Brendan to talk about the structural analysis of the plan.
So you can see on the right here sort of the structural configuration of our garage in the center. You'll see it's empty. That's where our ramp is going to be. We designed that separately, and you see that later on in the presentation. But the structural components within our parking structure are precast double T's, which act as the slab within the structure. They are all topped 3 inches of normal weight concrete topping, and the stems that are attached to those double T's will fit directly on the protruding sections from the beams, which will then sit on functions that we will in selecting our precast double T, we first had to determine the loads that would be present on them. Our third level has a wind, snow, and a live load present on it, and our second level will have just a live load. So in selecting our third level double T, the controlling load combination or load combination 3, LRFD load combinations, and that was 96 pounds per square feet. So we at a 58-foot span, we selected a 10 DT 32 plus 3 18 8 member, which breaks down to 10 feet in width. Double T, DT representing double T, 32 plus 3 representing the amount of height with 3 inches of additional topping, 18 representing the number of reinforcing strands within it, 8 representing the reinforcing strand diameter in 16 inches, and F representing the straight bar. This gave us a capacity of 118 pounds per square feet. However, the PCI handbook states that load capacity shown included dead load of 15 pounds per square feet for top members. So we had to subtract that from the 118 from the table, which gave us 103 pounds per square feet, greater than what we also did that for the second time. So in our beams, we use the process of first using the PCI load table to determine adequate beam dimensions, and then we custom design our own reinforcing steel. We have 2 different beams within our structure, an inverted T beam and an L beam. And then each one of those have different dimensions and reinforcing steel for the third level and the second level. So one thing to note, in the table you see on the following slide, 50% of the capacity shown in that table is assumed as a superimposed dead load according to PCI handbook. This means that 1/2 of the load shown in the table must be greater than the required load that we have. So in selecting our third level L beam, as is in red here, our required load is 96 pounds per square feet multiplied by 1/2 of the double T span, 29 feet, giving us a required load of 2,784 pounds per foot. As stated, the capacity in the table, 1/2 of it must be greater than that required load. So at a 40-foot beam span, we selected a 26 LB40, which breaks down into a 26 bottom width, B representing L beam, 40-inch overall height, which can be further broken down into an H2 of 16 inches and H1 24 inches, shown in the figure there. And this gave us a capacity of 2,860 pounds per foot, which is greater than required. Again, the same thing was done for our second level L beam, highlighted in red, and dimensions shown on the left. Our third level T beam, highlighted in red, showing dimension, and our second level T beam is highlighted in red. One thing to note going forward, in our structural analysis and design, we break our structure down into the 4 frames that span the length of our structure. We consider the 2 inner and 2 outer frames to be identical. And here you can see the frame object assignments, which show where the beams that we just discussed are located within each individual frame. And then here you can see the loads that are present on each frame. The point loads are a result of those double T stems fitting on the beams. The distributed load is a wall load that's present on all the beams. It goes around the exterior of our structure and then along the frame. And the wing loads are shown on those outside columns with the windward and leeward. One important thing to note is that all beams in our structure are simply supported.
So once we determine the dimensions of each member, we then design our custom structural steel inside each member. This example is a flexible steel design for a third level L beam. The process of which we determined a maximum required moment for hand calculation. Using SAT 2000, we were able to determine a minimum required amount of steel within each member. And by selecting 12 or 9 bars within steel, and the configuration you see the figure to the right. This satisfies our required amount of steel. Configuration shown gives us a design moment strength to be just over 1,700 kicks per foot, which is greater than required. This is also used with all beams throughout our structures. Shear design as well, similar to flexible design. For this, we selected our underfork stirrups. They're spaced at 9 inches, as shown in the figure to the right there. An important analysis was determining when the required amount of shear reinforcement was no longer needed. To do so, we used AWC, the fact shear force acting on the beam. At a certain point, the fact shear force acting on the beam is equal to half of the concrete force that the member is designed. At this point, no there will be no longer any shear force required. I believe we determined that to be around 17.5 feet from the column. The standard beam design is similar process for both flexible and shear. These beams are on the ends of our structures that connect each frame, and they support a wall load as well. We see our section area, flexible design, and our shear design in the far right over there.
So in designing our column, we first used SAT 2000 to determine adequate column dimensions. It was determined that we would need 3 different dimension columns in the entirety of our structure. The most typical column was a 20-inch by 20-inch column made of 5,000 psi concrete. Once we determined those column sizes, we then found a critical column for each column size for the column with the greatest axial and moment force on them. Once we determined that, we used PCI interaction curves to determine the longitudinal reinforcing steel we would need within it. In this case, the steel that we required was less than the 1% reinforcing steel to concrete area minimum. So we selected that minimum with the score number 9 bars. You can see here the AutoCAD cross-section as well as the tie spacing we also designed. Here's our 18 by 18-inch columns. Those are located in the corners of the structure. And you can see as well the cross-section and tie spacing. And our 24 by 24-inch column located at the ends of the ramps supporting the end bays. And as well, you can see the section and tie spacing. So in our ramp design, instead of using a double T to beam to column connection, we are directly supporting our double T's by columns spaced at 5 feet along the entire length of the ramp, as shown here. Every other one of those columns are then connected with beams that help support them laterally. We refer to these as H columns. And you can see here that there is a slight horizontal load present on each one of these. In this case, this is our most extreme H column, or the column with the tallest height. It's assumed that any column shorter than this, as the ramp declines, will also be adequate with the given dimensions. So for our beam, we selected a 14-inch width by 20-inch in height beam with 2 number 7 bars on both the top and the bottom of the beam, which is greater than the SAT 2000 required of us. And then for the columns, we selected 14-inch by 14-inch columns with 4 number 7 bars, also greater than the required from SAT 2000. And this gave us a max deformation of 0.15 inches in there. For our bracing, we decided to support those frames by inserting steel braces. We used the AISC steel construction manual to select the lightest W section available at our unbraced length. We determined that the W10 by 49 A992 steel. We then used multiple different configurations to determine which bracing configuration would result in the least deformation of the frame. You can see those in these images here, and our max deformation in the inside frame is 0.9 inches, and our max deformation in the outside frame is 0.08 inches. So our soil characteristics, we obtained a geotechnical report from SME that was conducted at the Haworth College of Business prior to its construction. Within that geotechnical report are 8 soil boring logs. We averaged those soil boring logs out to create one uniform soil profile, which we use in our foundation design. That is shown on the right here. The top 12 feet is a dark brown, medium dense sand clay fill with trace gravel. It was deemed in the geotechnical report to not be suitable for foundational support, and that is underlain by a light brown, medium dense, fully graded natural sand. Because that top 12 feet was determined not to be suitable for foundational support, we decided to use a driven pile foundation system with different configurations for each different column within the structure. For example, our 18 by 18 inch columns, we used 4 14-inch piles driven to 35 feet, and this gave us a factor of safety of 2.57, which was greater than the factor of safety of 2 we set out for. And you can see in the 20 inch by 20 inch and 24 by 24 inch columns, our factor of safety we achieved was greater than 2. In our ramp foundation, we used 1 12-inch pile driven to 35 feet per column, spaced at 5 feet along the length of the ramp. And this gave us a factor of safety of 2.19, again, greater than the factor of safety of 2.7. That I'm going to turn it over to Ferris. He's going to talk about standard.
So we were initially given these projects in the fall of 2021 semester. We began with short project planning. This semester is when we really go into the work with Brendan and Andy together and put design document development in January. And as they were wrapping that up, we began working currently together to develop a construction schedule and detailed cost estimates. We project construction to go from beginning of May to late August, with the owner moving late August to beginning of September. So this is our site logistics plan. As you see here, we have our construction site limits, our exterior surface parking lot, and our added green space. There will be one construction fence around these three areas of the lot. We also have our material laydown area, which will probably be delivering all material and equipment necessary to the project. And we also have personnel parking as well as field personnel, site offices, and we also would have a checkpoint of the units. This is our project schedule. As I stated, we begin early May and late August, with our movement late August, early September. As you see here, we have approximately 89 working days. It's always subject to change as we go through the working field. When this will take approximately 122 calendar days, so we have some flexibility for error in the case we need to work a few weekends. And so for a project of this stature, we would need a lot of trades on site so that we can run into potential conflicts. A way to subside these conflicts is to ensure subcontractor coordination. For example, we have 4 stairwells. We will need a 4-front curtain wall contractor, coordinator, the gas director, the steel director, and even the electrical for lights. We got to ensure the coordination is done just to make sure the project stays on schedule. Is not correct. So we developed a detailed cost estimate through RS means. There was too many line items to put it into a PowerPoint. So I developed a schedule of values breaking it down to 4 general categories. So we have our equipment costs, material costs, our labor costs, and all other miscellaneous, as well as our estimates of costs and all of these put together. As you see, our equipment costs approximately $200,000, material costs approximately $3.5 million, labor costs approximately $1.5 million, and all of the maintenance costs approximately $6,000, and the total project cost is approximately $5 million. That's what I'm Andy.
Important considerations for sustainability included environmental, social, and economic improvements to the location. We believe that environmentally this will decrease emissions as students will no longer need to sit idle waiting for a spot or driving around the parking lot looking for a spot. We'll also introduce green space, which we talked about before. Social improvements, we lower stress to students, which will help increase their student productivity. Don't start the monuments or disturbed or anything like that. And economically, we believe that this will increase the long-term revenue for Western Michigan University.
To conclude, we will be constructing a 3-level 420 space parking structure along 72W. This will increase parking capacity, student productivity, and environmental sustainability. We've had also the cost of $5.3 million in 22 calendar days to construct. And we'd also like to thank our sponsor, Andrew and Trey of WGI, our faculty advisor, Dr. Chow, and the design coordinator, Dr. Haynes. Questions?
You had calendar days scheduled there of 122. Did you say earlier it's like 88?
89 working days, 122 calendar days.
Does that include procurement of the precast?
That's just for construction.
So that assumes you've got materials.
Yeah, we would have to go on that prior to.
Like next year.
Yeah.
It's looking hard up to $5.3 million and we're still looking.
Was there any consideration or how we came up with the 3-level, thinking more of like you had there's an additional level with it then even more green space, or you could have made wider spots. Students parking at 8.5 foot wide spots probably
Yeah, so for this project, we consider just the 3 levels. We do consider in detail in our report that this could possibly lead to future, additions to the parking garage and increase in green space as well.
Yeah, for the scope of our project, building additional levels would obviously entail even more design.
Yep.
And we decided just to go to 3 levels, and that's our requirement, 50% increase parking capacity with also increasing some.
Did I hear you say you combined soil profiles and just kind of came up with a contiguous part?
Yeah.
The least or worst case.
We averaged, we had 8 soil blocks in my geotechnical report, and we just kind of graded and averaged all of those. So we could have 1 year. To use.
The extra plot they have to be done so we can put it in order.
Yeah, right. We don't have that.
For the sake of our project scope, it was to do stuff.
That's pretty, crane and logistics, site logistics. Do you guys look at any sort of staging and sizing, anything like that? Just scope of work.
We didn't include that in this.
I think the timeline can be
Yes.
student.
Absolutely.
So that'd be great.
Yeah. Yeah, I believe early on we had a slide and but we don't want to disrupt the parking coverage.
Okay, that's for this stuff.
Yeah.
Exactly. I would love to watch it being constructed in my office in HVAC.
Please ask, but it's just for students.
Primarily, yes. The current lot is for student use only.
Oh, okay.
So there are a lot of really for
Because as the old guy, there was no consideration in elevator.
Actually, we discussed the elevator. It's required to be anything over 3 levels. That would include an elevator. Well, we'll stay on top. It's not an actual planned project for us. Visibility, but everything is the second time Steve resigned to we will tackle this issue. Because, parking is an issue on many campuses. Any other questions for our jury?